Okay.
My dear students, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I'd like to welcome you all to our International Physics webinar. So, good evening to all here in Bangladesh, and a very good morning to all those who are watching this program live from USA. So, hope you are well and safe from Corona pandemic. So, as we know that we are staying in a Corona pandemic situation, this is very new experience for all of us. So, we are trying to adjust with this new normal situation. So we cannot continue our normal academic program inside the campus. So we have to start our online program. I think you have already come to know that the Department of Physics, Pabna University of Science and Technology, has started its online program, including online international physics webinar. And today, it's our 167 international physics webinar. We have with us here today Dr. Mingwu Jin, sir, Associate Professor, Department of Physics, University of Texas, Arlington, Texas, and he has already connected with us. So I'd like to welcome our speaker, sir. Good evening and good morning to your part, and thanks for accepting our invitation, sir. So before going to you, I'd like to introduce you with our student and all the viewers. So I think you have already come to know the title of this today's International Physics webinar. Title is the Physics Principle and the Deep Learning in Medical Imaging. And our speaker is Dr. Mingwu Jin, Associate Professor, Department of Physics, University of Texas, Arlington, Texas, USA. So Dr. Mingwu Jin received his bachelor degree in space physics and Master of Engineering degree in Communication and Information System from Peking University, Beijing, China, and PhD degree in Electrical Engineering from the Illinois Institute of Technology, Chicago, USA. His postdoctoral training was the Department of Radiology at the University of Colorado, Denver, UCD. He is currently Associate Professor in the Department of Physics, University of Texas, Arlington, UTA. Prior to this position, he held faculty position at both UCD and UTA. He has published more than 50 peer-reviewed papers and more than 80 publications. His research interests are in the image science and their application on the medical physics and space physics. His research is currently sponsored by NIA and DOD. And we can see his educational and professional background. So you can see that he has completed his bachelor and master's in engineering from the Peking University, China, and then PhD, Illinois Institute of Technology. And you can see that he has started as a research associate at Radiology, University of Colorado in 2007, and he stayed there up to 2009, and then he moved to in 2011 at the University of Texas as an assistant professor, and now he's working as an associate professor at the same university. So you can see his research and teaching interest. His research are in image science, including devices, model, reconstruction, processing and assessment, machine learning and data mining, and applying mathematical methods and physical principles to solve practical problems, particularly in medical physics and space physics. Teaching interest, medical physics, image science, college physics, and computational physics. And this is awards and honor. We can see here that he got the award from Faculty Department Leave, sponsored by the University of Texas, Arlington, and Trainee Abstract Award, sponsored by Organization of Human Brain Mapping, 15th Annual Meeting. First place awarded in the area of the communication and signal processing, sponsored by the Department of ECA, Illinois Institute of Technology, and the Best Student Paper Award, sponsored by the IEEE Nuclear Science Symposium and Medical Imaging Conference. And this is his support and funding from different organizations, and this is his publication, including books. So thanks for all of your patience. Now it's time to go to our speaker. So thanks again for accepting our invitation, sir. It's your time. You can start your session, sir.
Okay. Thank you very much, Dr. Das, for this detailed, introduction. It's my pleasure to give a talk at PUST for your students and the faculty. So basically I will talk about some physics principles and deep learning methods we did for the medical imaging. Okay, so before the talk, I want to talk a little bit about where I'm from and what about our university and the department. Actually, through this talk, I hope we can inspire some good students that to apply for the graduate program in our university. Okay, so basically, Arlington probably is more famous for the Arlington, Virginia, right? That's a more famous place. But Arlington in Texas is right between the Fort Worth and Dallas. That's two big names. Okay, people knows more about this Texas, right? And it has the Dallas Fort Worth International Airport. This is a very big airport that can get to most major cities in the world. So the traffic from the DFW to area to the world is very convenient. Okay, so Arlington, of course, is just right between the Fort Worth and Dallas. Then our university is right at the heart of the Arlington. So this star denotes our university. Okay. So then our university is Carnegie Research One University. That means the top tier of the research. Okay, so there are about 100 or so universities are categorized as the Carnegie Research One University. And also in the last year, we will promote to the Texas Tier 1 University. That's only, I think, 80 university in the Texas get that Texas Tier 1. So we'll get some special support from the Texas state government. And right now we have more than 57,000 students, okay, including the on campus and the online students. And we offer 180 degrees. Okay, so here this is the new University Park that we hold the commencement there. Of course, also the some university games, and this is planetarium. Actually, it's the biggest one in the Los Texas area. That is just basically is running by our physics department. Okay. So down to our department, actually, our department is the strongest research on campus. Okay, so we have over 5 million research expenditures every year, and the operating budget is 2.2 million. Okay, we have 28 tenure track and tenured professors, and numerics laboratory and the computational facility and a motion shop. So here is the high performance computing facility. Okay, you see these cables, and this is just a lab. I think it's for the condensed matter physics and planetarium, and this is the science hall. Okay, where the department office locate. Okay. So the research areas are including high energy physics, condensed matter physics, astronomy. Those three are pretty traditional, subjects of the physics. We also have 2 new physics track. That's medical and nanobiophysics and space physics. Okay, so those are 2, actually provide the students a great, career path. Okay, because not everyone will become a theoretical or nuclear physics physicist, right? So this kind of special applied physics provide great opportunities for the students to get some professions in the hospitals or in the LASA. Okay, so for the medical and nanobiological physics group, we have 4 professors. We have Professor Wei Chen, me, Professor Amir Shamaradi, and Professor Yujie Qi. So our strength is on the nanoparticle development, experiment, medical imaging, and simulation. Okay, so here just shows some things we are doing here. Okay, from the medical imaging to the nanoparticle to the simulation of the DNA changes during the radiotherapy. Okay, so that's just a brief introduction of our university and department. Okay, so we have this website. If you are interested, you can just look over. If you are interested, once you graduate, you are encouraged to apply a PhD program here. Okay. So without further ado, let's get to our topic, the physics principles in the medicine. Okay, the first slide want to contribute to the Nobel Prize that's related to the medical image. Actually, in the modern, radiology, all those workhorse equipment from the X-ray radiograph, X-ray computed tomograph, nuclear medicine, that includes scintigraph, SPECT, that's single photon emission computed tomography, and the PET, that's a positron emission tomography. Okay, and the magnetic resonance image, MRI, they all come from the great physics discoveries. Okay, so of course the first one, you probably know that Wilhelm Röntgen discovered the X-ray in 1895, and that won him the first physics Nobel Prize. Okay, so this picture just show he took the X-ray picture of his wife. That's a very first X-ray picture. And of course, there also ultrasonography was not awarded a Nobel Prize, but awarded a Lasker award. That's the highest award in medicine, except Nobel Prize. Okay, you can say all those is just founded on the physics discoveries. Okay, and of course, this picture shows that Marie Curie, he's the only woman won Nobel Prize twice, right? One in the physics, the other in the chemistry. This is in 1915. She was riding on his little Curie, that is the mobile X-ray vehicle. So actually, this mobile X-ray vehicle took the pictures of millions of the wounded soldiers, okay, because they can take pictures to find whether the bone is broken or not, okay. So those are all, you say, the physics actually really lay a foundation for the modern radiology, okay. That's the, very useful for the diagnostic or prognostic of the, of the medicine, okay. So yeah, that's just a little bit of history. I want to inspire that, this physics principles really, really useful in the medicine, okay? So first part of the talk, I will talk about applying imaging physics to improve tomographic reconstruction. Tomographic actually from the Greek, okay? Tomo, that means the cross section, and the graph means the image, okay? So before the X-ray, we don't know how can we see through a human body, okay? But once we have the X-ray, then if we actually can take a proper measurement, we can reconstruct the human organs inside the body, okay? Here comes the story of the Alan Cormack. He was a nuclear physicist, okay? But he did some part-time job as a medical physicist. That's from 1950 to 57 at the Cape Town University, South Africa. Okay, it's just 1.5 days a week in radiology. Okay, and then actually his work as a medical physicist needed to his winning of the Nobel Prize in 1979. Okay, so actually in 1963 and 64, he published the the work representing of function by its non-integral with some radiological applications. So his work was not noticed for several years until the Sir Godfrey Hounsfield invented the first CT scanner. Okay, he had this scanner, but once from the CT scanner data, actually he has to contact the Alan Comac for help. Okay, so his algorithm is actually is just suited for the CT scanner. So that's why, you know, both him and Hansfield won the Nobel Prize in 1971 for inventing the CT scanner. Okay, so it's interesting that actually there is a mathematician named Redan already described this kind of transformations called a Redan transform in 1970. So, but at that time, you know, internet is not as good as nowadays. Okay, some work is really hard to, you know, disseminate to the world. Okay, it's kind of, you know, Alan Comac reinvented the Redan transform and won the Nobel Prize, but this was actually studied a long time ago. Okay. So here is the picture that I visited the Mayo Clinic, and this is first CT scanner in the United States. Actually, the Mayo Clinic purchased the first CT scanner from the Godfrey Huntsfield, okay, from the United Kingdom. Okay, so I just feel honored to take a picture with this first CT scanner. Okay. So let's get some like basic CT reconstruction problem. Okay, so we have the X-ray tube that will generate X-ray that will pass through the human body and detected by the detector. Okay, so those green lines shows X-ray. Okay, they just traveled in the straight line by assumption. So we can have this Bill lambda law, right? So the I0 is just the incident X-ray intensity. Once it passes through the body, it's get attenuated. So it has this exponential decay. Okay, this is the line integral, this fxy, that is a linear attenuation coefficient that distribute of the body, right? That's why we have the xy. So what we can do, so basically you can at the certain angle, projection angle, you can have many rays, you will have a profile, right? So how can we get this PXR phi? So we actually can do a log, you know, transfer between the I0 divided by the I9. This one, left side is what we detect at the detector, right? So once we do this log transform, then this PXR phi, we call the projection data, is equal to the line integral of the attenuation coefficient. Okay, so this is how we get data. Then do further mathematical analysis, we can transfer this line integral into the double integral. So we just needed to multiply this attenuation coefficient by a, you know, delta function that just denotes a line. Okay, that is just cross this projection line. Okay, so this is called Redan transform. That is the contribution from the Alan Comac and Redan. Okay, so of course, if you want to reconstruct the image, actually you can do a inverse Redan transform. Okay. So another, actually the better way is that we can use the Fourier transform. So this means capital P, that just means the Fourier transform of the lowercase p. Okay, so if you do the Fourier transform, then you say the Fourier transform of this projection data, this PXR phi is a PVXR phi. So this is a Fourier transform. Then this actually is equivalent to the Fourier transform of the image domain along this line. Okay, this line is parallel to this projection. So this actually is called the Fourier slice theory. So this is the foundation of the currently most used reconstruction algorithm in the clinic, that is filtered back projection. Okay, I will talk it later. So of course, we cannot just get one projection to reconstruct the whole image. We have to, collect this, projection around the patient. Okay, 180 degrees at least. Okay, so basically we have this is called a sinogram. So horizontal is this XR and the vertical is the phi. So this is called a sinogram because you see those patterns is very similar to the sinusoid function, right? So this actually is the sinogram of this shape log and phantom. Okay, this image. So basically, for the CT scanner, we will get the observations like this. Then we want from those observations to reconstruct the image like this. Okay. So as I mentioned, the field back projection reconstruction is the most popular reconstruction methods. So you say once we had the projection data, we actually can know the frequency domain representation of the image, right? So you say each line represents the one projection at a certain angle. So if you have many, so you say you actually get the data point in the frequency domain. Okay, so we can write that non-integral as linear function because in the computer you have to digitize things, right? So we have this m times f. F is the image we want to reconstruct it, and the p is the observation we got. So that is a linear function. So M unit is called a system matrix, for any imaging system. So for the FPP reconstruction, we just do high pass filtering of the projection. Then we do a back projection. That's just a transpose of the system matrix. We get the reconstructed image. Okay. So why do we need this high pass filtering? Because look at it here. We have actually more simple at the center that is the low frequency component. So basically you have the observation that put more weight in the low frequency component. That's why that will smear the edges of the object. So we want counterbalance that effect. So we needed to do some high pass filtering. So let's say use these two figures to restate this process. So for the data collection, we have this forward projection, right? So that basically is expressed by the P equals M times F. So you have the different views of this project, of this object. So for the reconstruction filtered back projection, we just first do FFT, then high pass filtering, then do an inverse FFT, then do a back projection. So you will say we want to do this high pass filtering to enhance the edge. So we'll get a reconstructed image. Okay. So of course you need many views to get the better reconstruction. Okay. More view will lead to a better reconstruction. Okay. So of course, in theory, you want to get a perfect reconstruction, you need infinitely more observations. But in reality, you just need to have a certain numbers of the projection. Okay, so you say this reconstructed image is very close to the original image. Okay. So, but we know the X-ray actually is harmful to the human body, right? So at the Röntgen invented the X-ray. First, they used it for the imaging. Then later they found this adverse effect from the X-ray. Actually, that will cause the breakdown of the DNA, right? That will kill the cells. Okay. So for the image, we want to collect less data. That means the less radiation and shorter examining time. That will increase the clinical workflow. Okay, so there are many motivations to lower the radiation dose. Okay, to still get good reconstruction results. So that's actually is our focus for last a few years. Okay, so for unit cities reconstruction, we need like hundreds or thousands of views to get a good FPP reconstruction. But you know, for each view, you will shoot the X-ray at the patient, right? So how about you know, we just you know, reduce the projection views? Okay, so we'll say what will happen. So this is the original Ship-Logan fountain. So if we use the 360 views and use the FPP, we get a pretty nice reconstruction. Okay, but if we reduce the projection view to 72, then you will start to see some like strike artifacts. Okay, you still see a little bit, you know, details inside this phantom, right? But if we further reduce it to 36 views, that's just 1/10 of the original views, right? Then you say the very severe artifacts are shown and the details inside cannot be seen anymore, okay? So the question is, can we lower the number of views while maintain the good images? Okay, so yes, but not with FPP. We need some like more, you know, advanced, you know, reconstruction algorithms. So we have to use properties of the image, for example, sparsity and also iterative reconstruction. Okay. So first, you know, we will address the incomplete data problem. Okay, actually in 2006, you know, Cadence Donoghue, they had this theory of the compressed sensing. Okay, so then if the signal is sparse, then the fewer samples are needed to reconstruct the original signal. Okay, this really breaks down that Lax's sampling theory. Okay, so for example, here we have this phantom, right? If you check the non-zero pixels, that's about 50%. So we say this is not sparse, right? The original signal. Then if we calculate the variation image, so basically you do this just as do the horizontal and the vertical difference of the labeling pixels, you will actually get the edges of this phantom. Then now you find this variation image, you just have 5% of the pixels have non-zero value. So it becomes sparse, okay? So then we can basically transfer this image from its original form to the variation domain. Then we actually can say that the total variation is small, okay? This is a constraint we can use to help our reconstruction with incomplete data. Okay, so there are two general methods to do this kind of thing. First one is unconstrained optimization. So the first thing, of course, you always want to reconstruct the image. So that's m times f is close to your observation. That's p, right? So this is called data fidelity. And the second term is just regularization, right? For example, that is in the last slide, we want to transfer it into the variation domain, then want to the total variation is small, okay? So that is the unconstrained optimization. You have to tune this parameter beta, okay? So we can also do constrained optimization. So we have this regularization function. We want it to be minimized and also subject to two constraints. The first is data fidelity constraint. And the second is that every attenuation coefficient should be non-negative, right? So we have this three kind of convex set, okay? So then the solution is just the intersect of three convex sides, C1, C2, and C3, okay? So the latter one actually provides an easy way to determine the reconstruction parameters than the unconstrained optimization, because it's better, okay? There is no much theoretical way to determine what is the best beta, okay? So we developed this full sequential projection onto convex sets, you know, method, that's FS-POX, okay? So we just do these three projections in order. So first is we use algebraic reconstruction techniques that to fit that data fidelity term, right? And the second is just zero setting. If we find any negative values, just set as a positive or as 0. And the last one is using the parameter dual hybrid gradient algorithm to solve that TV minimization problem. Okay, we just repeat those 3 projections until the solution converges. Okay, so this pictures two just shows some like toy problem. Okay, if we want to find just one point intersect of 2 convex sets, okay, it will take a long time to converge. So you can see here, after 300 iterations, we get still more than 10 to the minus 2 error. But if we use this convex set as our solution, okay, of course the solution is larger, then you will see the error will drop very quickly, okay. At 35 iterations, that's 10 to minus 15 error. So more drastically, if we have like a good path, you say maybe you have just 2 steps, you can reach your solution. Okay, so that's really very efficient, algorithm. So here are just some reconstructed images from a head cadaver. So the first row is with the 1,200 views. Okay, that's a lot of data, right? And we cut down that views to 160. We use the TV parks. That's some methods from the other group, and also the FS parks from our new methods. Okay, so this is just a washout display. And here you will see that septal of the nose, right, is much better recovered by our method. And also there are some sinus holes, is also better recovered by our method. And of course, at the washout, you say original image, you should have some like sinus hole here. And TV parks, just totally missed those points, but our method recovered them. Okay. So that's just a little bit about the reconstruction algorithms. Okay, let's talk about some problems with the combine CT. Okay, so there are 2 types of CT. First is the multi-detector CT. That is actually for the diagnostic purpose. Okay, it have X-ray tube and a detector inside the bowl. They can rotate very fast. Okay, they can be as fast as like 3 revolutions per second. So it can quickly scan through the patient. And another one is this combine CT. You say this is the source, this is a detector. They are, actually like in a C-arm, is just slowly rotate the patient. This is used in the radiation therapy, okay, to just locate the tumor location to align with the treatment plan. Okay, then after that, this is a linear accelerator will generate a high energy, X-ray that will be used to treat the tumor from different locations. The problem with the CBCT, not only the data collection is slow, and also the detector is the flat panel. It's not the aerial detector. Then you say the X-ray will pass through straight away, right? And but sometimes it gets scattered once, or maybe get multiple scattered. So the location of the detected event doesn't have a straight line relationship to the X-ray source. Okay, so in this case, you say it depends on the detector field of view and also the thickness of the human body. Okay, the scatter to primary ratio, that means how much the scatter, dominant your detection will becomes more and more. For example, if you have field of view 30 and you have a thickness of the tissue is 30 centimeters, the scatter actually about 6 times of the primary photons. Primary, that is follow this straight line, right? So that really breaks down the good geometry assumption. Okay, you assume all those X-rays traveled in the straight line, right? So then, if you based on that wrong assumption, you do a reconstruction, you will get this kind of image. Okay, But for the multi-detector CT, the detector is narrow, and also they have some like collimator, so you will get you don't get much scatter event, so you get really a truthful reconstruction. But CT, if you don't compensate for the scatter effect, you will get a lot of this kind of shading artifacts. Okay, so that lowers the contrast of the soft tissue, and also if you want to calculate the dose, those wrong CT numbers will give you inaccurate calculation. Okay, so there are different methods to deal with this problem. For example, the anti-scatter grid is like some like a collimator, right? It's just lay before the detector. So then you say that this just some like a high Z material, for example, lead, right? It will absorb those scatter, photons. But this will cause, decrease the photon detection. If you want to keep the same amount of the detection, you have to increase X-ray intensity. That will cause more damage to the human body, right? That's not good. And also we can use some like a static blocker, but that will decrease the field of view, and also the estimation of the scatter is not accurate. And or we can do Monte Carlo simulation. That's a computational intense. Okay, so what we can do, actually, my colleague at the UT Southwestern Medical Center developed this technique called the moving blocker method. So we put some like blocker between the radiation source and the object or the patient. Okay, so you say now you blocked part of the X-ray to the object, right? So that's good. Okay, you lower the radiation dose, but the data you collect is not complete. So to solve this problem, actually, we make the blocker move. Okay, so at the different projection angle, you have a different blocked areas. So then you can put them together. We can use the compressed sensing reconstruction, get good reconstruction. Okay, so here we have this blocked area. Okay, based on the assumption is blocked by this kind of lead strip, right? Should have no detector, low detection, but you will get some detection. That actually comes from the scatter. So those blocked region actually used to estimate the scatter component. Once we estimate that, we can remove it from our observation, right? Then we can reconstruct nice, clean images. So here is a method that we use to estimate the scatter. Actually, before the original method, we just use the current view to estimate the scatter. Later, we say, yeah, that will cause some problem. Then we can use the multi-view. We can use several adjusted view to get a better estimation of the scatter component of the CPCT. So reconstruction is very similar to the previous, full sequential Parkes method. Okay, so but this is just a different one. So here is just some example I showed here. This is the pelvis phantom. We have 3 ROIs, and multi-detect CT gives the kind of a gold standard here. And if we don't do the scatter correction, you will see the CT numbers are way off. Okay, so this is the image from the reconstruction without scatter correction. This is the ground truth from the MDCT. And if we do the single view, you will see at the this area, at the edge area, there is a not intensity change. You have a lot of artifacts come out. But for our method, we effectively removed that artifacts. Okay, so you see the CT numbers is close to the ground truth. Okay. So most recent work we actually did is 4D moving blocker thing. So we actually applied this moving blocker to acquire a sequence of the images. So that is a respiratory motion of the patient. So left side is the phantom, okay? So it has the respiratory motion. So this, of course, the transverse, coronal, and the sagittal views of 3D phantom. So for the conventional reconstruction, we use some like 4D reconstruction, no scatter correction. So you say there are a lot of shading artifacts, but if we do our, those kind of moving blocker to estimate the scatter, we can effectively remove those, artifacts, and also we reconstruct very faithful motion of the lung. Okay, so let me switch the gear to the nuclear medicine. Okay, it's similar. We do the reconstruction. So it's different from the X-ray CT. The radiation source is not from the outside; it's inside. Okay, so we have this kind of called radio tracer. This green hexagon is about some like pharmaceuticals. Okay, that is like some drug will combine with some metabolic or physiologic, process in the human body, and also we tag it with some radioactive source. Okay, this is like an image reporter injected to the human patient. After a while, this drug will bind to a certain organ. Then we do the image. Okay, so tomography imaging. Then we do reconstruction. So here we just overlay this emission tomography, that is a color image, onto the CT image. CT image provides you the structure, and this image just provide you, this color image just provide you the functions of the organ. Okay, so here let me focus on the single photon emission computed tomography. That's SPECT. Okay, so basically you say here we have this human body. You will have the radio tracer distribution inside the body. So this tracer will have a high binding with the heart. Okay, so then we have this is called the gamma camera. It is composed of the collimator, detector, and the photomultiplier tube. Okay, so we get the observation GI, and of course we want to reconstruct the FG. Okay, so in this case, we want to reconstruct those tracer distribution that reflects the body physiology instead of the anatomy. Okay, the physical factors that will degrade the image quality are, distance dependent resolution, low sensitivity, attenuation, and scatter. Okay, so of course, all the collimator that used to just dictate the detection, the directions of the photon. Otherwise, we don't know which is the direction of the photon we detect. Okay, so that is use this is the purpose of the collimator. Okay, so the reconstruction problem is to get the image F, that's tracer distribution, from the projection data G. Okay, so actually we modeled those physics in the SPECT. First is the distance dependent point spread function. So if you have a source is closer to your detector, you actually get a narrow point spread function. That means your resolution is better. Further away, you get a large blow. Okay, and also you get attenuation. That is the photon is not following a straight line, right? It could be absorbed at some point inside the body, or maybe scattered away. Okay, so that's attenuation, or it could be scattered, and so the detect of the photon is at a different place. So attenuation will decrease your detected photon, and the scatter will increase it, but in the wrong place. So that will lower the contrast. The last problem is the noise. Okay, so the up figure shows if there is no noise, if we have kind of some phantom, we have very nice projection data. But in reality, we have this Poisson counting noise, right? This photon is coming, the detector is just count how many photons it received. So you will say it's a very noise observation. So all those things we have to, take into consideration into our reconstruction. So we have this forward image model. Okay, so in the system matrix H will take into consideration of the distance dependent point spread function and the attenuation. So we want to reconstruct some uniform resolution, right? And the scatter, we just have this additive term. And since this is a random process, we just say we have this expectation of the observation should follow in this forward projection model. Okay, so here's the effect of the different degradation factors. This is original phantom. If there is no the physics degradation factors, we have just do the FPP reconstruction. You will see very nice reconstruction, right? Very close to the original image. But if we have the distance dependent resolution, attenuation, and scatter added to the projection, you will say the image is distorted a lot. Finally, if we add the Poisson noise, now you say this image is not like the original image at all. Okay, you probably just say something like a rough, shape there, right? So we have to deal with all those kind of the problems. Okay, but how about for the moving organs, for example, the heart? Okay, then heart is motion is just constantly beating, right? So in order to catch that beating and avoid those motion artifacts, right? So we can actually synchronize our data collection with electrocardiogram. So you can divide those heart cycle into, in this case, 8 gates, okay, or 8 phases, or sometimes 16 phases. So then in each phase, we can treat it as a still. Then now we want to reconstruct a series of images instead of just one image. So that will further, reduce the photon counts in each phase, right, or each gate. So that is even challenging. Okay, so then I will skip the mathematics here. Okay, so basically we will propose like a 4D reconstruction and using the maximum or posterior criteria to reconstruct all the gates for one cardiac cycle. So most important part, we will enforce smoothness among the motion trajectory. Okay, so basically during the reconstruction, we will do the imagery reconstruction and also estimation the motion of the heart. Okay, so here's the results. So this is the short axis of the heart. This shows how we get this part of the image, okay, the orientation. And the true, this is a busy image, okay? So let me focus on the choose and also this ST121. So this is actually the method used in the clinic. They do just the FPP reconstruction and one-to-one temporal filtering. So basically they will do some like average between the current phase and the previous and the later phase. So 3 images, the center one, you just take a weight 2, the other just take weight 1. So you say the shape of the heart is not well maintained, and also you have, say, a lot of like kind of boiling artifacts. So all 4D reconstruction with compensation for the attenuation and the scatter showed much better reconstruction, right? You will say the uniformity of the hard wall is much better, and also the the motion is not giggly like the other images. Okay, so this is all 4D reconstruction for the cardiac SPECT, and of course that is just for the phantom. This shows the real image, the images for the real patient. So you will say this is a clinic. Actually the doctors are used to those kind of images. We're blurry, right? But we can get a very sharp reconstruction. Okay, that's has a very nice depict of the hard walls. Okay, so of course we also did some like low dose SPECT research. We just reduced the radiation dose of SPECT by 75%. Then we found our method still better than the clinical method. So this one is just use the relative root mean square error to denote the reconstruction accuracy, and also this lesion detectability that represents how the doctors, detect whether there is a disease or not. Okay, so AZ is the area under reserve operating curves. So that's really measures how you detect whether there is a lesion or not. Okay, so you say for this one you want to have a higher value. Okay, so all methods, that's a black bar, it always stands out, and also it does not affect a lot by the reduced radiation dose. Okay, so basically you can inject less radio tracers to the patient and reach the same diagnostic accuracy. Okay, so that's first part. That really tells us, if we understand the physics principles and use it in a wise way, we can get good image quality and lower the radiation dose to the patient. Okay, so for the second part, I will talk about the deep learnings for the image reconstruction, denoising, and computer-aided diagnosis. Okay, so here is the toy problem. Okay, for the projectile motion, we want to calculate the level horizontal range. So basically, object is eject at the level, then with the initial velocity and the angle theta, right? So we want to say where it will land. So yeah, this is a very simple physics problem. It's just second order differential equation, right? We know the acceleration due to the gravity and also the initial conditions. Then we can get the solution. That is just v square sine 2 theta divided by g. Okay, so then actually we can use the neural network method. For example, we can shoot this object 1,000 times. So using the different v and the theta, right? So then we can actually get those data points in this 2D space. So this is the velocity, this is the angle. So then we can construct a neural network. So here we just have a 2-layer with the output layer. So then we actually can feed this function, v square sine 2 theta divided by g. Okay, we can feed actually very accurately, using this just 2-layer, 2-hidden layer, neural network. Okay, so this is basically the deep learning. If we have enough data, we actually can avoid to solve complicated, mathematical equations, right? And just let the neural network give you the answers. Then goes back to our reconstruction, right? So I forgot to mention, for those iterative reconstruction, we constantly compare our reconstructed image, then project to the projection domain to compare with the observation, right? So that takes a lot of time. In 2018, there is a paper in Nature actually divides our neural network to skip that complicated reconstruction component. Just use the neural network. Okay, if you train it, then basically you can fit in your observation, then you get the reconstructed image. So basically here is the synogram of this image. So how can you just after the training to transfer this synogram into this image? Okay, so basically they use 3 layers of fully connected network and 2 convolutional network and 1 deconvolution layer. So we actually did this test. Okay, we trained this random transfer in the lateral images. Okay, then we do the test image. So this is the original image. This is the reconstruct from the trained neural network. Yeah, it works nice. Okay, not quite the same, but still good. Then we used it on our XCAT phantom. That's more like a human phantom. Then we tried different parameters, but the reconstruction results are not as good as our iterative reconstruction based on the physics. Okay, So of course, that is just because this all-to-map network structure is not optimized. So later there is a work, okay, it's more complicated design of neural network is called ICT-LET. It's not our work, it's from other colleagues. So they break down the, the physics in the reconstruction into the different layers. So the first 5 layers just suppress the noise, and the next 4 layers, they do just the extraction of the high-level figures and features. Then the last is just the transfer from, the next layer is transfer future space to the image space. Then the last 2 layers just combine all the views. So basically you say they will get the reconstruction actually is much better than the compressed sensing reconstruction. So this is really encouraging because the network training is time consuming, but once you train the network, the reconstruction becomes very fast, okay? So of course, this is still active research, area. So we will do this. Okay. So another way is that we can lower the radiation dose, then the image becomes noisy, right? So we can do an image domain denoising using some deep learning method. This is a residual encoder-decoder convolutional neural network. Is from the other group to and to denoise the low-dose CT image. Okay, we used unsupervised learning. It's called cycle-consistent generative adversarial neural network. Okay, cycle-GAN. So what we do is that we want to do an image transformation from the low-dose CT to the full-dose CT. So this is a forward, right, mapping. And then because it's unsupervised learning, we don't have the pairs of the low-dose CT and the full-dose CT. So we have to do this kind of transfer back from the full-dose CT to the low-dose CT. So we have this pathway, that's the pathway, go back. So we have to compare those. Okay, you transfer back, then go here, you should go back to the full-dose CT. Okay, so of course, another red pathway is just transfer from the full dose back to the low dose. Okay, we actually don't care about that, but it's just we want to train the network in a balanced way. Okay, that give us better results. Okay, so here is just show some results. We actually tried. This is a full dose image, and this is just quarter dose image. Is much noisier, right? We just show this magnified neural region, and this is from the red CNN. That's a deep learning, denoise method. Yeah, it's effectively removes the noise, but you see the texture is quite different from the full dose CT image. So there. The second row is from 3 variants of the cycle-GAN. Okay, so they just have a different network structures, and then they have a slight different, results, but the performance is a little bit different. But the training times varies a lot. Actually, the fastest one is the GAN circle. It has only like 100,000 parameters. The other two have millions of parameters. Okay, but the GAN circle seems the best network that achieves the best quantitative results. That's a peak singular to noise ratio and structural similarity index. Okay, it's here. So basically, yeah, unsupervised deep learning method actually is better than the supervised deep learning methods in this case. Okay. So the last one I think is just we did some like machine learning methods for computer-aided diagnosis of the Alzheimer's disease. Okay, actually we are interested in the mild cognitive impairment. That's the early stage of the Alzheimer's disease. We designed some like memory task for the patient to perform during the MRI scan. then we get those 14 subregions in the hippocampus. That's very important to the memory of the human brain. So we use some like radio basis network. Actually, we can get a very good, separation between the normal control and the amnestic MCI. Okay, but this data, we just have, I think, about 8 patients for each group. So that is really needed. We need more patients to generalize this result. Okay, so later we also used some like booster tree to using the structural MR measures to get the different stages of the Alzheimer's disease. So we have the health control MCI that we're going to convert to the Alzheimer's disease and the Alzheimer's disease. So the accuracy actually is in the diagonal from this confusing metrics. Okay, so you say for the health control and the Alzheimer's disease, we can get a very accurate, prediction. But for the middle stage, there is still a lot of work to do, right? The accuracy is not that good. Okay, so we also recently did some like deep learning methods, but I'll just skip that. Okay, to conclude, so accurate modeling of the physics of the medical imaging is important to improve image quality or reduce the radiation dose without compromising quality and the clinical value of the medical image. And also deep learning is becoming a powerful tool for image reconstruction, enhancement, and computer-aided diagnosis. Okay. So at the end, I want to take home that ultimately is the physics discovery and breakthrough that push the frontiers of the medical image field. And also deep learning provides an alternative and effective way to solve many challenging problems in the field. Okay, hope you bear with me. So this slide just thank you all my collaborators from the different institutions and the funding sponsors. And the last, this is our first group lunch like 3 weeks ago. Okay, we locked down like for more than a year. Okay, finally everybody get vaccinated, and we just yeah, you still see the marks on the table. Okay, but we have lunch, we have to take it off. Okay, so if you are interested, you can check my website for our projects and publications. Thank you. I'm ready to take any questions.
Yeah, thank you, sir, for your wonderful presentation, sir. I think our students have learned a lot of things about the physics principle and deep learning of medical imaging. We know that in new medical technique, actually the medical imaging is very important for any treatment. So you are doing a great job, and I think our students have learned a lot of things about this, and maybe in future some of our students will feel interested in this research. So we have got few questions. If you allow, you can start our discussion session, sir.
Yes, sure, please. Yeah.
Okay, so first question. So which is better, CT scan or MRI?
That is a $1 million question. Okay, so basically CT is much faster than the MRI. Okay, this is no doubt. And of course, CT will cause the ionization radiation. Okay, that's not good. MRI is just non-ionization radiation. That's good, right? And also for the soft tissues, MRI will provide a better contrast. Okay, so in general, CT is faster and cost effective. Okay, and the MRI is slower but better, soft tissue contrast. So it depends on the application. Okay, in some case, CT may not give you the things you want, so you have to go for the MRI. But the MRI generally more expensive and slower.
Yeah, but in terms of radiation dose, maybe MRI is better.
Yes, MRI definitely is better. But you say for the CT scan, if we can lower the radiation to less than, say, 1 millisievert, then you say the effect, maybe we can ignore that. So we say you can treat that not ionization radiation, right? So yeah, that's why we push the limit of this radiation dose lower and yeah.
So there is another similar question. So what are the basic difference between MDCT and the CBCT?
Oh, the difference, I don't have a video here. For that MDCT, that is used in the diagnostic radiology. So it actually, the source and the detector inside the bowl, so it can actually rotate very fast. So I said as fast as like 3 revolutions per second. So it can acquire the data very fast, and also the detector, of course, now they make a detector larger and larger, so it have a larger coverage of the human body. If they just have a very little coverage, then they have to do some kind of helical scan, right? When the patient bed is moving, then they do the scan. Okay, so it's very quick and also less affected by that scatter. But for the CPCT, as I showed that animation, you have a flat panel detector that's a large size. Okay, no collimation, so any photon can be detected, and also that is mounted on the C-arm, so that is used for the radiation therapy. So you say that actually mounted on the treatment machine. So it cannot rotate like that fast, okay? It rotates like in 1 minute to 2 minutes to finish one revolution. So it's very slow, okay? So usually the quality is not as good as a multi-detector CT. But if we do, advanced reconstruction, we can get a pretty close image quality to the MDCT, okay? Dr. Josh, you mute yourself. I cannot hear you.
Sorry, sir. So do you use Janfer for Monte Carlo simulation or other program for Monte Carlo simulation?
Oh,
Janfer?
For Monte Carlo simulation, yeah, we for the SPECT, we use the software package called CNET. That is developed by some professor in Sweden. Okay, so that they have those modules. Okay, they actually designed those gamma cameras that is exactly as the same as the clinical scanner. And of course, the most popular software package is called GATE. I think that that's a gene for emission tomography, GATE.
Yeah.
Okay, so that one is a more generic one. So I haven't looked at whether they provide those customized modules. Okay, if they don't, so you have to design those modules. Okay, that may take a longer time. Okay, but I know that GATE was used a lot by the community. And for the CT simulation, we have called GCC. That's some like a GPU-based simulation for the X-ray. That is from our colleagues at the University of Texas at the Southwestern Medical Center. So actually, we are very close. So if you have some students interest to come here, we have a lot of collaboration with the radiation oncology, radiology. So we have access to their machines and their softwares, software packages. Yeah, that's very convenient setting here. Yeah.
Thank you. So we have another question, and this may be the last question. What is the difference between the supervised and unsupervised learning?
Okay. For the supervised learning, basically you have to have those paired images. For example, you have one low-dose CT image, you must have the same set of the full-dose CT. So basically, unless you can do some like simulation to get those kind of image, otherwise you have to scan the patient twice, right? Once with the low dose, once with the full dose. So usually that's not good for patients, right? They don't want to get 2 scans, just for the research purpose. Okay, so for unsupervised, learning, that we have the, low dose. Some patients we just use the low dose protocol, and the other patients we use the full dose. So we don't have this correspondence of the low dose CT and the high dose CT. But the physics principle is same, right? We just have this attenuation coefficients of the human body. Okay, so even they have a different shape of the organs, maybe slightly different of the material composition, right? But still, that will give you some like high-level features that are similar. Okay, so that's why I think the unsupervised learning still works, okay, because they are deal with the same kind of physical measurements. Okay, that's actually what inspired me at the beginning. Okay, that cyclogram is developed in the computer science, is not for the medical image. So we say, yeah, this probably can use for the medical image too. Okay. So basically, for the unsupervised learning, we don't have a detailed labeled data. For supervised, we need that label or alignment of the 2 sets of the images.
Okay, sir. So thank you for your wonderful presentation and nice discussion session, sir. So it was a very great webinar with you, sir, and thanks for giving us this opportunity to arrange such an important webinar with you, sir.
Okay,
So,
thank you so much.
yeah,
My
thanks again, and we would like to say thanks on the behalf of the Department of Physics, Pabna, University of Science and Technology, sir. It's my pleasure, and actually it's my honor and privilege to host you in our international physics webinar, sir. So thanks
yes,
again.
definitely, yeah. Encourage your students, just apply our program if
Yeah,
they're interested.
of course.
Yeah, thank
Of course,
you.
they would apply. Okay. Bye,
Okay,
sir.
okay, bye bye.